Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. My contribution of the world's fastest computing to mathematical knowledge made it possible to invent a new computer and create new mathematics. In 1989, I was in the news for discovering how to harness the world's slowest processors and use those processors to solve the most difficult problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. In algebra, the most difficult problem was to discover how to solve the largest system of equations arising when executing detailed computational fluid dynamics codes, such as global climate modeling or petroleum reservoir simulation, and executing those codes across the millions of processors that outline and define a supercomputer. In the 1970s and 80s, my mathematical quest was to become the first person that could solve such initial boundary value problems and solve them across the slowest processors in the world. At 8:15 in the morning of July 4, 1989, I discovered that the world's fastest computer can be built with the world's slowest processors. And I invented the supercomputer technology and did so across the slowest processors in the world. That new supercomputer paved the way and became the precursor of the world's fastest computer that now computes with millions of ordinary processors. Parallel supercomputing was my mathematical quest for how I can cross the new frontier of knowledge, of how to solve an unsolved system of equations in algebra. My quest was to cross that frontier and conquer today's mathematical challenges. My quest was to solve previously unsolved problems and quickly compute the most compute-intensive problems in large-scale computational fluid dynamics, such as simulating the spread of contagious viruses inside Japan's Tokyo subway, where 3.1 billion passengers a year are packed like sardines. In 1989, it made the news headlines that an African supercomputer genius that worked alone in Los Alamos, New Mexico, USA, has invented how to solve the largest system of equations in algebra and invented how to solve those systems by parallel supercomputing them or solving many equations at once, and solving those equations across a new internet, that's a new global network of 65,536 coupled processors. I visualize my computing machinery as a small copy of the internet. I, Philip Emeagwali, is that African supercomputer scientist and the computational mathematician that was in the news in 1989. I was in the news for inventing how to solve the largest system of equations during the most important applications in algebra. One such application is in computational fluid dynamics. The poster girl of large-scale computational fluid dynamics is the supercomputer petroleum reservoir simulation that must be used to nail down the exact locations of crude oil and natural gas. Such extremely fast calculations can only be executed across an ensemble of millions of processors that occupies the space of a soccer field and that simulates an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep. An oil field is about the size of Abuja, Nigeria. The Agbami oil field of Nigeria was discovered in late 1998. Agbami was Nigeria's second largest deep water oil field. Agbami is second to the Bonga oil field. Agbami oil field is located 4,900 feet or 1.5 kilometers away from the coastal shores of central Niger Delta. It has a peak oil production of 250,000 barrels per day. Why is the supercomputer important to Nigeria? 1 in 10 supercomputers were bought by the petroleum industry. The most powerful computer in the world costs the budget of a small nation. The fastest computer is the heavyweight champion in the world of petroleum technologies. The supercomputer is used to pinpoint deposits of crude oil and natural gas. Fastest computing is my contribution to modern algebra and to the petroleum industry. I'm the subject of inventor reports because I invented how to execute the world's fastest calculations and perform them across an ensemble of the slowest processors in the world and solve the most compute-intensive problems at the crossroad where new mathematics, new physics, and the world's fastest computing intersect. I invented how to solve the most compute-intensive problems and solve them across a new internet that's a new global network of 65,536 coupled off-the-shelf processors that shared nothing and that each operated its operating system. By 1986, I realized that the most difficult problem in petroleum reservoir simulation, namely the solution of a parabolic system of partial differential equations, was at its granite physical and mathematical cause, an effort to forecast the weather, but to forecast it backwards in time. This backward technique is called hindcasting and is used to forecast, or rather to hindcast the weather and hindcast or reforecast up to 7.7 miles or 12.4 kilometers below the surface of the earth, and hindcast it across an oil-producing field that's up to twice the size of the state of Anambra, Nigeria. Because I was both a geologist of the late 1970s and a meteorologist of the early 1980s, I could translate that compute-intensive problem and translate it across physics, calculus, algebra, and computer science, and translate it from the primitive equations of meteorology to the 9 Philip Emeagwali equations of mathematical geophysics. This new field of study is described as the subsurface porous media multi-phased fluid flow modeling, executed across millions of off-the-shelf processors that were identical and coupled. In 1989, I could solve the most difficult problem arising in supercomputing. I solved it by deeply understanding and drawing on the mathematical metaphors between the extreme-scaled computational fluid dynamics problems in both meteorology and geology. My contributions to mathematics had their calculus and algebra roots on how I reformulated the hardest problem in subsurface geology. I reformulated that mathematical problem and did so in a meteorological context. Furthermore, I parallel processed that mathematical problem, and I did so across a then world record ensemble of 65,536 processors. Not only that, I visualized those processors as outlining and defining a small internet, and as tightly circumscribing a globe and encircling that globe in the manner computers encircle the earth. My 1989 discovery changed the way mathematicians solve their most compute-intensive problems. In my new way, the most difficult problems in physics, mathematics, and computer science are solved across an ensemble of millions of processors instead of within one processor, as was done in the old way. The toughest problems in mathematics are solved on supercomputers purchased for the Nigerian petroleum industry. The prototypical most difficult problem in supercomputing was to compute at the fastest speeds the motions of crude oil, injected water, and natural gas that were flowing across an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep. An oil field is about the size of my hometown of Onitsha, Nigeria. The Bonga oil field is located off the Nigerian coast and 75 miles or 121 kilometers southwest of the Niger Delta. The Bonga oil field was underneath an average water depth of 3,300 feet or 1 kilometer and covers 60 square kilometers and produces both crude oil and natural gas. The Bonga oil field began production in November 2005 and was projected to be abandoned in the year 2022. In the 1950s, 60s, and 70s, mathematical physics textbooks classified the governing system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations as parabolic. Often, when parabolic partial differential equations are discretized to yield a system of partial difference equations, the resulting system of equations of computational linear algebra is tridiagonal. Its associated tridiagonal matrix has non-zero elements on the main diagonal and on the two diagonals below and above the main diagonal. Why was my contributions to mathematics in the news in 1989? My contribution to mathematics was this. In the 1980s, I changed the way we look at the calculus and the algebra behind the compute-intensive simulations of the motions of crude oil and natural gas that were buried 7.7 miles or 12.4 kilometers deep and buried across an oil field that's about the size of a town. My mathematical discovery was that the world's fastest computer can be built with the world's slowest processors. My invention was the cover story of top mathematics publications, including the May 1990 issue of the Siam News, which was the flagship publication of the Society for Industrial and Applied Mathematics. I'm the subject of school essays on famous mathematicians because I changed the way mathematicians solve their most compute-intensive problems in algebra. My contribution to the mathematical knowledge and supercomputer technology used to nail down the exact locations of crude oil and natural gas is this. I paradigm shifted from a parabolic system to a hyperbolic system of partial differential equations that governs the initial boundary value problem. And I paradigm shifted again from tridiagonal to diagonal system of equations of computational linear algebra, from the parabolic and hyperbolic systems, respectively. I invented the system of equations of computational linear algebra that must be used to recover otherwise unrecoverable crude oil and natural gas. In 20th century algebra, such systems were most often tridiagonal. Such tridiagonal systems are unsolvable in parallel or impossible to solve by dividing each into a million or even a billion lesser compute-intensive problems that can be mapped onto as many processors and then solved with a one-to-one correspondence and solved at once or in parallel. Because I was computing and communicating across a global network of 65,536 processors, I saw computational mathematics differently. Because I saw mathematics differently, I thought differently and invented differently. Why did I invent the 9 Philip Emeagwali equations? My original derivations of the 9 Emeagwali equations are lengthy. However, they are fully described in my YouTube channel named Emeagwali. In essence, my point of departures from the mathematical derivations of Darcy's equations that govern subsurface geophysical fluid dynamics were that I accounted for both the temporal and the convective inertial forces. I've posted the mathematical details across my 1,000 video clips that I've also posted on YouTube. For clarity, I detailed my mathematical derivations in closed caption prose. My mathematical quest was to discover how to solve the differential initial boundary value problem, not for how to solve the algebraic discrete problem from that initial boundary value problem. My quest wasn't for how to solve the initial boundary value problem and solve it as an applied mathematician who solved it on his blackboard. That quest for an extremely fast computer was for how to solve the never before solved larger scale problems in computational linear algebra and solve them as a modern computational mathematician who is sitting astride his global network of 64 binary thousand motherboards. Each motherboard was a computational metaphor for his as many or 65,536 blackboards. I invented a system of 9 partial differential equations of calculus and then invented my 9 partial difference algorithms, or the complete step-by-step instructions each of my 65,536 processors must execute as the condition for solving the difficult mathematical problem and solving it at the world's fastest speed that made the news in 1989. I used my new algorithms to discretize my system of partial differential equations, which in turn yielded my system of 24 million equations of computational linear algebra. Those were the longest equations in the mathematics of 1989. With my new algorithms, those equations became diagonal instead of tridiagonal. It's impossible for my new system of 24 million diagonal equation of algebra and the old system of 24 million tridiagonal equations of algebra to be mathematically equivalent. I visualize my problem as identical twin problems of algebra. The diagonal and the tridiagonal systems of equations of computational linear algebra arose from different initial boundary value problems with the same boundary condition, the same initial condition, and the same mathematical and physical domains. However, each initial boundary value problem had a different governing system of partial differential equations at the frontier of calculus. The diagonal and the tridiagonal systems of equations of computational linear algebra are equivalent in their physical essences, and they are equivalent in the physical sense that both arose from a hyperbolic and a parabolic system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations, respectively. Both systems of partial differential equations of calculus encoded the same set of laws of physics. My new diagonal and the old tridiagonal systems of equations of computational linear algebra approximated the same difficult mathematical problem of extreme scale computational physics. My new diagonal and the old tridiagonal systems of equations of computational linear algebra are as different as identical twins from the same egg and sperm and from the same genetic materials. Just as identical twins are clones, my new diagonal and the old tridiagonal systems of equations of computational linear algebra were clones. They are not algebraically equivalent, but they arose from the same difficult mathematical problem of extreme scale computational physics. Metaphorically speaking, they arose from the same egg and sperm. Scientifically speaking, they arose from the same set of laws of physics. My invention of fastest computing, which occurred on the 4th of July 1989, changed the way mathematicians solve the most compute-intensive problems in algebra. The cover stories of mathematics news journals read by leading mathematicians celebrated my mathematical discovery as a breakthrough that makes it possible for high-performance computational mathematicians to achieve speeds in supercomputing previously considered impossible. In 1989, mathematicians celebrated my discovery of the fastest computing, and did so because it heralded the end of their old arithmetic paradigm of solving one compute-intensive problem at a time. And it marked the beginning of the new paradigm of concurrently solving millions of sets of compute-intensive problems and solving them at once. On the 4th of July 1989, I achieved a supercomputer breakthrough. I used the 65,536 slowest processors in the world to reduce 65,536 days or 108 years of time to solution to merely 1 day of time to solution. Furthermore, I discovered that the most compute-intensive problems in algebra that in turn arose from calculus could be solved across a new internet. Not only that, I invented that new internet as a new global network of 64 binary thousand processors that were coupled. Each processor had its dedicated memory that shared nothing, but were in dialogue with each other. My high-performance computing experiment, which I conducted across a new internet, that's a new global network of 65,536 processors, led to my discovery that elucidated why the world's fastest computer must be powered by billions of processors. The reason my discovery of how to execute the world's fastest computing was in the June 20, 1990 issue of the Wall Street Journal was because it opened the door to the fastest supercomputers that were powered by over 10 million processors. I discovered how the oil and gas industry now harnesses the fastest computing from the slowest processors and do so to nail down the locations of subterranean hydrocarbons. My discovery that millions of processors can be used to solve the most compute-intensive problems is the new knowledge used throughout the petroleum industry. It's the most critical technology now used to pinpoint deposits of crude oil and natural gas and used to recover them. It's used from the producing oil fields of Nigeria to the oil fields of Angola. I used the largest system of equations of algebra that defined the most compute-intensive problems in physics as the backdrop for my experiments across my ensemble of 65,536 processors. I used those equations as my supercomputer testbeds. In the 1970s and 80s, fastest computing across the slowest processors existed only in the world of science fiction. My contribution to computer science was that I challenged the established truth and turned that science fiction to reality. That truth was the widely held belief that the slowest processors in the world cannot compute together and do so to solve the most compute-intensive problems in algebra and in extreme-scale computational physics. and solve them at the fastest recorded supercomputer speeds. The recognitions which I received from the supercomputing community in 1989 and later was the first time such skepticism over parallel supercomputing was overcome. In the 1970s and 80s, 25,000 supercomputer scientists tried to parallel process and do so across processors and computers. They gave up. They dismissed my attempts to solve the most difficult problems via parallel processing as impossible. I proved them wrong. In an often cited paper published between April 18 to 20, 1967, the IBM supercomputer designer, Gene Amdahl, formulated Amdahl's law. Briefly, Amdahl's law predicted that supercomputing across the slowest processors will forever remain an enormous waste of everybody's time. Seymour Cray designed 7 in 10 supercomputers sold in the 1970s and 80s. Seymour Cray agreed with Gene Amdahl. Using the chicken as his metaphor for the slowest processor and the ox for the fastest processor, Seymour Cray asked the supercomputing community his famous question: if you were plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens? Regarding the ox versus a billion chicken debate, I visualize the grand challenge problem of supercomputing as breakable and chopped up into 1 billion less challenging problems, each akin to a few wheat seeds in a large field. My theory was that a billion hungry chickens can eat up 1,000 billion wheat chickens and eat them faster than one hungry ox. Parallel computing is a century-old theory that existed in the realm of science fiction. My contribution to computer science made the news because my invention of the first supercomputing across the world's slowest computers turned that science fiction to reality. On the 4th of July 1989, the century-old theory of harnessing 64,000 human computers became timeless and new again. It was never old. When I came of age in the 1970s, the computer world was the mouthpiece of the information technology industry. A state-of-the-art survey published in the June 14, 1976 issue of the Computer World quoted the leaders of thought in the world of supercomputers as unanimously agreeing that harnessing thousands of processors will be too, quote-unquote, large and clumsy. The title of that Computer World article summed up the skepticism towards parallel processing and my later discovery of the world's fastest computing across the world's slowest processors. The pessimism was embedded into the title of that article, which was, quote, Research in Parallel Processing, questioned as waste of time, unquote. My discovery made the news because it was computing's equivalent of breaking the sound barrier to create a sonic boom. Before my discovery, fastest computing across slowest processors was an intellectual barrier that no human dared to cross. I was in the news because I was the first person to cross that intellectual barrier. I was the first person to scale the pinnacle known as the world's fastest computing. On July 4, 1989, I became the first person to plant his country's flag in the then unknown territory of the supercomputer as it's known today and as it's expected to be known tomorrow. I used 65,536 processors to demonstrate how a mammoth supercomputer can be built from a billion processors. I discovered how harnessing up to a billion processors will enable the world's fastest computer to have the horsepower it will need to address the grand challenges of the scientific world. I researched as a lone wolf because my supercomputing milestone was believed to be unachievable. Parallel processing powers every supercomputer manufactured today. The supercomputer is to science what the microscope is to biology. My scientific discovery, which occurred on July 4, 1989, was that the world's slowest processors can be used to solve the most compute-intensive problems in science, engineering, and medicine. My discovery of the central essence of the world's fastest computers made the news headlines because it changed the way we look at the modern computer. I discovered how to reduce 108 years of time to solution of the most difficult problems in large-scale algebra and computational fluid dynamics, and how to reduce that time to 1 day of time to solution. In the 1970s and 80s, I was mocked, ridiculed by vector supercomputer scientists, and offhandedly dismissed because I claimed to have discovered how to reduce the times to solution of the most compute-intensive problems, such as the high-stake global climate models, and reduce them by a factor of 1 billion across a new internet that's a new global network of 1 billion processors that shared nothing. I was mocked for claiming my discovery of the world's fastest computing and claiming it when it was considered impossible to reduce those times to solution and do so by a factor of 8. When confronted with such a compute-intensive problem, the vector supercomputing community joined ranks and tore holes in my then unsubstantiated theory. I theorized that the slowest processors could be harnessed and used to compute faster than the fastest supercomputer. My unorthodox approach to solving compute-intensive problems is called parallel supercomputing. Until my experiment of July 4, 1989, the parallel supercomputer was not a the parallel computer was not a supercomputer. It was then a million times slower than the supercomputer. In 1989 and in Ann Arbor, Michigan, my character was malign because I was conducting research on parallel supercomputers, a technology then dismissed as pseudoscience. I distributed 6 copies of my 1,057-page supercomputer report to scientists in Ann Arbor, Michigan. All 6 copies were thrown into the wastebasket. To their surprise, a few weeks later, it made the news headlines that I had won the equivalent of the Nobel Prize in Supercomputing. I won that prestigious prize for my supercomputer invention, which I fully described in my 1,057-page research report that they're trashed into the waste baskets of Ann Arbor, Michigan. After I won what was referred to as the Nobel Prize of Supercomputing in 1989, the intellectual fireworks exploded. I didn't kill any person, yet I was subjected to a Galileo trial that was computing's equivalent to the O.J. Simpson trial. If they were to accept my discovery, they must forget many things they've learned, such as their belief in white intellectual supremacy. I solved the most difficult problem at the crossroad where new mathematics, new physics, and the world's fastest computing intersected. That accomplishment was the reason I was compared to the likes of Albert Einstein, Pythagoras, and Euclid. In retrospect, and for racial and intellectual reasons, I was not taken seriously as a black mathematician who was equally at home in physics and computer science. I was confident because, as far as I knew, I was the only person in the world that devoted almost the entire decades of the 1970s and 80s to supercomputing across processors. I acquired the specific sets of skills and knowledge within mathematics, physics, and computer science that in turn would have enabled me to solve the most difficult problems in supercomputing. First, I was black and African, and therefore grossly underrated with respect to Albert Einstein. Second, I was a lone and unsalaried supercomputer scientist whose research was grossly undervalued by both the funding agencies and the prize committees. They automatically rejected my submission. They automatically rejected any submission from a black African scientist. Third, I was misperceived as only a one-dimensional mathematician or physicist, never as a three-dimensional polymath or a triple threat that was at home in computer science. Fourth, it was not widely known that I had been continuously supercomputing since June 20, 1974, on one of the world's fastest supercomputers that was at 1800 Southwest Campus Way, Corvallis, Oregon, USA. Fifth, I was also trained as an astronomer, meteorologist, and geologist. Therefore, I was not timid about crossing disciplinary boundaries and doing so when pursuing the elusive answer to the biggest question in supercomputing. That question was this: how do we compute fastest with the slowest processors? In supercomputing, the most compute-intensive problem must be breakable into a billion pieces that can be solved at once and solved across a billion processors that each was self-contained and shared nothing. Solving the most difficult problem across the world's fastest computer is like putting a jigsaw puzzle with a billion pieces together. My invention of how to compute in parallel or compute many things at once was mentioned in the June 20, 1990 issue of the Wall Street Journal. It took me the prior 16 years to discover how and why computing across the slowest processors makes the fastest computers fastest. My discovery opened the door that elevated the parallel supercomputer to a new supercomputer that's up to a billion-fold faster. and that's used to solve the larger system of equations in many fields. Such grand challenge problems range from computational fluid dynamics to computational medicine, such as simulating the spread of contagious viruses across Onitsha market where social distancing rules are not enforced. In the 1980s, there were 25,000 computational mathematicians who also desired to know how and why a multitude of processors makes the slowest computers faster and makes the world's fastest computer fastest. The reason those mathematicians gave up on massively parallel processing was because their textbooks warned them that supercomputers built with a billion processors will forever remain an enormous waste of everybody's time. If any of those mathematicians or physicists or computer scientists had the knowledge that I had, they would have been famous for solving the most difficult problem in supercomputing that I solved in 1989 and that made the news headlines. Because everybody ridiculed and rejected the theory of solving many problems at once, parallel supercomputing was abandoned. That was how I became the lone full-time programmer of 16 of the most massively parallel supercomputers ever built. Today, the most powerful supercomputer hosts up to 10,000 programmers. What differentiates I and the other 25,000 vector supercomputer programmers of the 1980s were these. I invented how to harness an ensemble of 65,536 off-the-shelf processors that were coupled and that shared nothing. In 1989, it made the news headlines that an African supercomputer genius in the USA had invented how to harness 65,536 processors and invented how to use them to solve the most compute-intensive problems called grand challenges. Such problems arise when addressing some of the world's biggest problems, such as simulating the spread of COVID-19. My invention opened the door to the technique of parallel and distributed algorithms and the companion technology of the massively parallel supercomputer. Parallel computing is the core knowledge that makes the impossible to solve possible to solve and makes it possible to solve up to 1 billion mathematical problems at once. I, Philip Emeagwali, was that African supercomputer scientist in the news in 1989. The grand challenge of computing was to be the first person to solve the most difficult problem and solve them at the world's fastest speeds, but solve them across the world's slowest processors. A reason it was called a grand challenge problem was that the 25,000 vector supercomputer scientists of the 1980s and earlier couldn't solve it. The reason vector supercomputer scientists couldn't experimentally invent fastest computing across the slowest processors was that they were merely reading about how it's impossible to harness 65,536 processors. In the 1980s, it was believed that it will forever remain impossible to harness millions of processors and use them to cooperatively solve the most compute-intensive problems at the frontiers of knowledge in science, engineering, and medicine. those 25,000 naysayers had the opportunity I had to solve the most compute-intensive problems, which were central to supercomputing. All they needed was the brain power. Each of those 25,000 vector supercomputer scientists knew that the invention of supercomputing across the slowest processors with their key to discovering a gold mine. My contribution to the development of the supercomputer is the reason I'm the subject of school essays on inventors and their inventions. I'm Philip Emeagwali. Thank you. Thank you very much. Thank you.
Insightful and brilliant lecture.